Our modern municipal water systems owe much to the inventiveness of ancient Rome. To provide water to crowded cities throughout the Roman world in Europe, Asia, and northern Africa, the Romans built some 600 aqueducts over an 800-year period. Water flowed by gravity alone over tens of miles from springs and other mountainous sources, beneath the earth in vaults, through tunnels in mountains, and across valleys and channels atop arcades of arches. The aqueducts of ancient Rome supplied clean, fresh water to public fountains, baths, and sporting events, and even to private homes. The Romans placed much pride in their aqueducts as marvels of their superior civilization. They recognized the importance of abundant potable water to maintain their health and prosperity. 11 aqueducts supplied water to some 1 million people in Rome itself. The remains of the aqueducts have survived wars, earthquakes, scavenging, and the collapse of the empire. Not only were the aqueducts marvels of engineering and hydraulics and models for modern water systems, but also wondrous works of architecture and art, particularly when aqueducts cross valleys and arcades. The arches of different aqueducts, and even the same aqueduct in different locations, different in terms of building materials, color patterns, the use of cornices, and the numbers, heights, and widths of arches. Despite their relative mundane utility, their picturesque quality, and in some cases enormity, even amazed the Romans themselves. The original Lego models on display exemplify some of the diversity and design of the ancient Roman aqueducts. Although no attempt is made to be dimensionally correct, the models demonstrate how the aqueducts worked and why their ruins still evoke a sense of awe. This model is a cross-section of a Roman aqueduct system. The system begins at a mountain spring. There, water is captured in a spring box and carried in a channel over a valley by an arcade of arches. Water flowed strictly by gravity. On the other side, the water's journey continues through a tunnel constructed through a mountain. For most aqueducts, water was tunneled underground for most of their length. It was only when valleys were encountered did they rise up high on arcades. Shafts were periodically constructed for workers to enter the subterranean tunnels to make repairs and to clean out the deposits. When crossing steep or long valleys, Romans used inverted siphons to carry the water across the valley. Along the route, the water would fill pressure tanks that helped control the gradient, filter tanks to allow sediment to settle out, and finally distribution tanks. The water then went by pipe to public fountains and baths and to private villas of the wealthy. Sewers carried wastewater away. The two models illustrate how water for aqueducts was typically captured. Where springs emanated from rocky slopes, a spring box or tank constructed of stone could be set on the slope to capture the water and direct it to an aqueduct channel. In soil slopes, wells were dug below the water table. The wells were connected to tunnels to drain the water. These methods are still in use today for municipal supplies and bottled spring water. The next two models illustrate how water was carried below ground in carved tunnels in rock or in vaults buried beneath the ground. For most Roman aqueducts, water flowed mostly underground like water mains today. Subterranean paths offered protection from the elements and enemies. Vertical shafts were constructed along the aqueduct to access the subterranean channel. A typical subterranean channel was about 1 meter wide and about 2 meters high, and coated with waterproof plaster, a Roman invention. These two models are of the Marcia Aqueduct in the southeastern suburbs of Rome at Aqueduct Park. This is one of 11 aqueducts that were built over an 800-year period to provide water to Rome. At the park, the aqueduct is just emerging from the ground, as illustrated in the first model, as it entered the Tiber River Valley approaching Rome. Note how the arches are very low to the ground, just 1 to 3 feet in the second model. The aqueduct was constructed in 144 to 140 BC. Toward Rome, the arches increase in height. Romans used arches because they saved on construction material and can hold heavy loads. The Romans often combined aqueduct paths by building one aqueduct on another. 2 other aqueducts were built on top of the Marcia at Aqueduct Park. The Tabula, built in 126 to 135 BC, and the Julia, built in 33 BC. Their partial ruins can be seen in the accompanying picture. Viewed today, the ruins of aqueduct channels and arcades are usually uncovered. When they function, they were covered with wood planking, stone blocks, or concrete vaults. These are 6 models of the Claudia and on top the Anno Novus aqueducts, both constructed between 38 to 52 AD. The small and large models of regularly spaced arches illustrate the ruins in Aqueduct Park in Rome. The aqueducts are on top of stocky rolling arches made of stones of volcanic rock. In Aqueduct Park, the aqueduct arches are some 7 feet wide, span over 15 feet, climb from near ground level to several stories high, and extend over a mile. Further towards Rome, the aqueduct takes on different styles. The third tall model shows the aqueduct arcade at a park, Parco di Tor Fiscale, closer to downtown. There, the arcade is composed of rock veneered and perhaps reinforced with bricks and exhibits tall, alternating single and double slender arches. When the aqueducts reach the Aurelian Wall on the southeast side of Rome, they are on top of a white travertine gateway, the Porta Maggiore, that passed over 2 basalt-paved ancient roads. One of the roads led to Capua, where the Spartacus revolt began. The bar stretched between the arches illustrates the average slope of a Roman aqueduct channel, only 2¼ feet of height change per 1,000 feet of length. Over the 5-foot distance between the arches, the height of the bar drops by only 0.135 inches. The height change is the thickness of 1 flat Lego brick from the bottom to the top of a stud. Although this looks like a Roman aqueduct, it is the High Bridge in New York City. The bridge is part of the old Croton Aqueduct and crosses the Harlem River connecting the Bronx and Upper Manhattan. Plagued with waterborne diseases from tainted city water supplies and insufficient water to fight fires, New York completed the old Croton Aqueduct in 1842, modeled after the Roman aqueducts. The aqueduct carried water 41 miles, mostly underground from a countryside reservoir by gravity, with a gradient of only 13 inches per mile. It served the city from 1842 to 1965. The bridge is the oldest bridge in the city. A branch of the Aqueduct Marcia was built on top of the pre-existing Arch of Drusus. This branch was constructed to supply water to the nearby baths of Caracola. The arch can be seen at the southern gate of Rome. Let's examine some aqueducts outside of Rome, in other parts of the Roman world. The Pont de les Ferreres Aqueduct, aka Francoli Aqueduct of Tarragona, Spain, is a massive 85-foot tall, 2-tiered structure made of stone. The diameters of the arches on both tiers are the same. Unlike most other aqueducts whose columns are straight or change abruptly in size between cornices, the piers of this aqueduct widen gradually in a series of regular steps near the bottom. In Segovia, Spain is one of the largest, tallest, and well-preserved Roman aqueduct bridges. The bridge is constructed of 2 tiers of massive double arches, on top of which is the aqueduct channel. The top of the aqueduct channel reaches a height of some 94 feet. As a testament of the quality of Roman engineering, the aqueduct functioned from imperial times to the 1920s. The aqueduct and the Old City were listed as an UNESCO World Heritage Site in 1985. The Roman aqueduct in Seville, Spain, is thought to have been constructed during the period when Julius Caesar conquered Spain between 68 to 65 BC. Amazingly, it was in continuous use from then until 1912, when most of the aqueduct was destroyed. Only small sections remain. The portion of the aqueduct modeled has 2 tiers of double arches. Unique to this aqueduct is the fan-shaped small arch between the larger ones. Another unique feature is the embedded stone water pipe running parallel to the channel at the bottom of the top tier. The Milagros, or Proserpina Aqueduct, is constructed mostly of brick and consists of 3 tiers of arches that are almost 100 feet high. To help support the tall structure, lateral buttresses were used. The bridge artistry included creating a striped pattern of color by placing brown bricks at regular intervals between the mostly buffed colored bricks on each column of the arches. The aqueduct channeled water from a reservoir the Romans built in the 1st century AD. Although the aqueduct ceased operating when the Roman Empire declined, the dam still functions and the reservoir continues to supply water today. The origin of the aqueduct in Halkita, Greece, is debated: Roman, Turkish, or Venetian. The aqueduct arcade is constructed of widely spaced double arches on tall, straight piers and is made of stone blocks. The aqueduct in Kavala, Greece is not Roman. However, it may have replaced a Roman aqueduct. It was built in the early 16th century. It is an example of copying the Roman style in both engineering and design, but with some unique character. It is a massive structure composed of two tiers of arches. The upper tier has two smaller arches between the larger arches, presumably to reduce load while maintaining strength, but they also provide an artistic uniqueness and flair to the overall design. The aqueduct in Moria, on the island of Lesvos in Greece, shares a striking similarity to the Milagros aqueduct in Spain. It consists of three tiers of arches, but built without the buttresses. Although the channel was composed of brick, the rest of the aqueduct was made from marble blocks. A unique feature of this arcade is the arches appear as bent beams rather than topped with bricks to form a flat upper surface. The Pont du Gard Aqueduct Bridge in Nîmes, France, is the largest Roman aqueduct in the world. It spans across the Gardon River and reaches a height of over 160 feet. It is a three-tiered arcade on a grand scale, with arches up to 80 feet wide. On top of the lower tier is a bridge. Despite the arcade's massiveness, the channel on top of the upper tier is only about 4 feet wide and 6 feet tall. Can you imagine building the impressive structure whose blocks weighed over 6 tons each, with no hydraulics or electric power? Talk about Roman know-how. The Romans built several aqueducts to supply water to the seaside city of Caesarea Maritima in Israel. This is a photo of the high-level aqueduct. The aqueduct is really two aqueducts running side by side that were built at different times. One during Herod's reign between 37 and 4 BC, and the other during Hadrian's time between 132 and 135 AD. Despite over 100 years of engineering development, the latter aqueduct was constructed to match the former in most dimensions and style. The main difference between the aqueducts was in the channel. Water in the older aqueduct was carried within a covered channel. Terracotta pipes carried water in the newer channel. Perhaps the Romans used pipes to reduce evaporative losses in the desert climate. Typically, Roman aqueduct arches got taller as the valley deepened. Here, the arch dimensions were held constant, but what changed was the addition of step-like platforms of stone beneath the aqueduct footings. Perhaps that was done to reduce the load to prevent settlement, given that the aqueducts are on a sandy beach. The ruins of Pompeii provide an opportunity to examine a Roman water system in detail. Water flowing from the Augustan aqueduct, destroyed when Vesuvius erupted in 79 AD, discharged to a tank that filtered and divided the water. Water from the aqueduct flowed through a tunnel in the back of the tank. When it entered the tank, it encountered filters that screened sediment. Then, using gates and channels, the water was divided into 3 pipes that carried the water to different places in Pompeii. One channel led to the fountains, another to the baths, and the third to private villas. The heights of the gates were adjusted such that if a drought occurred, water to the villas would be curtailed first, then the baths, and lastly the fountains, which supplied drinking water. To control pressure, they had water towers distributed around the city at elevations below the diversion tank. Water would flow from the diversion tank in lead pipes to a lead water tank on top of a brick tower. The overflow would drain into fountains. Water would flow from tower to tower and to water fountains, villas, and baths throughout the city. In addition to providing drinking water, aqueducts brought clean water to baths throughout the Roman world. The baths of Caracalla, built in the 3rd century AD in Rome, was one of the largest bath complexes with hot, warm, and cold baths, a large swimming pool, gyms and exercise rooms, libraries, and gardens. The water was heated by circulating hot air beneath the floor of the baths. The interior of the baths was decorated with arches, marble walls and columns, mosaic tiled floors, and marble statues. The baths occupied 26 acres and accommodated some 1,600 bathers. To supply water to the baths, a branch of the Marcia Aqueduct, the Antoniana Aqueduct, was created. About 100 years after the Romans sacked Carthage, they rebuilt the city in their image. To provide water to the new Roman city, they built one of the longest aqueducts, the Sahun Aqueduct. Over 15 cisterns, over 300 feet long, were constructed for water storage. How and if the aqueduct and cisterns were connected is still a mystery. The model shows the aqueduct, a transverse cistern, perhaps a settlement tank, and only 3 of the many cisterns that still survive. Long abandoned as storage tanks, the remains of the cisterns have served as stables and even homes throughout the years. Like modern water systems, the Romans also used pipes to distribute water. Large cut stone, tongue, and groove pipes were used when the water in the aqueduct was pressurized. Terracotta and lead pipes were used to distribute water from the aqueducts to fountains and buildings. The cost of water to a private villa was determined by the diameter of the lead pipe that connected to the villa. Roman water systems constantly flushed, which prevented lead buildup in the water. The picture depicts part of an inverted siphon system the Romans used when their aqueducts needed to cross wide or steep-sided valleys. The siphon works like a U-tube. The model is a working model used to demonstrate how the inverted siphon works. Water flows from an aqueduct to a header tank. As long as the water level at the header tank is higher than the receiving tank across the valley, water will flow across the valley and up the other side. To carry the water from tank to tank, the Romans used stone or lead pipes. By locating a series of header and receiving tanks, they could control the water pressure and maintain a relatively low hydraulic gradient. Romans liked their bread. To grind wheat into flour, they used grinding wheels turned by slaves. However, there are a few locations that show they also used water power. The Lego brick model is designed after the mills at Barbagal in France. The mills were built in the 4th century AD. Water was supplied by an aqueduct that also supplied drinking water to the city. The mills at Barbagal are estimated to have produced enough flour to feed over 12,000 people a day. This is a model of a Roman water wheel that existed in Ostia, at the mouth of the Tiber River in Italy. Most of the aqueducts had spring water sources. Where spring water was not available but clean streams were present, and where the city was uphill from the source, the Romans were known to construct large diameter water wheels to lift water to tanks or aqueducts for distribution.